Hi everyone. In this week we will start a new topic about the probability theory and its application on the machine learning or the artificial intelligence, okay? Probability theory and its application. First of all, we need to summarize all the terms in here, just like this one. Up to now, we have dealt with the data that is mapped into or between input and output, okay, with specific exact values of itself. Okay. So we drive the mapping between the input and output, but how come, or how we can do this? For example, we can build to the what, or we did build the regression, right? Just like this one. We proposed a model, for example, y is equals to the what 3.3 times x plus 2, okay? This is the linear regression. But we have always a data of the what, the x and y. Or in the neural network or the perceptron model, we build to the what x2 and x1 input mapping in here, just like this one, and we create or store the data in different ways. Just this, okay? And so we draw a hyperplane by using the what, the perceptrons, and then we can assign to the what, the 1 and 0. This is called logistic regression, right? We map all the data into the what, 1 and 0 in here to classify the whole the data. Or we have built to the what, to the multi-layer perceptron, guys, okay? x1, x2, and so maybe we have the XOR problem in here, just like this one, and so we draw the 1 line and 2 line. This is 2 neuron in here, and also we assign to the map of the 1 and 1, or 0 and 1, or 0 and 0, or 1 and 0 in here. This is the MLP case, okay? But in every case, we utilize the training data and also model sigmoid or softmax or something like that, okay? And also we have the output, but every time this is absolute, okay? And this case created with the what, with the supervised or unsupervised learning, okay? But just remember that this generates always to the what, absolute value or exact. But what if we want to build to the what, not to absolute or exact values of these outputs? For example, we want to design the classification algorithm based on the what, the logistic regression, but we don't want to need to do what the exact values of the 1 or 0 And so, how we can utilize or build this algorithm based on what the non-probability theory or the mathematics. And so, we should call it the probability theory. We can identify all the outputs in terms of the what? Probability. Maybe in some case we can say that this is the what the X class if the output of the logistic regression is greater than the 0.5. Okay? And so how we can utilize or implement this algorithm on the what? On the machine learning or the artificial intelligence, we should use the probability theory. And so basically it scales the output, scaling the output, but every scale may be different meaning of this one, or the one scale is creating to the what? The different meaning of the our data set. Okay? But in order to understand these problems, we need to create this diagram. Problem can be defined with the what? With this one. Assume that we have a logic like 0 and 1. Okay? And so if we drive these axes, Cartesian axes, and so this is the 0 point, and so this is assigned to the 1, this is assigned to the 1, and so we can draw the what? Two lines, and so this is the what? This is the exact value in here. Okay? And so this is the 1 and 1. And also this is the what? This is the two lines with intersection point. This is the meaning of the geometry. Based on the what? Based on this decision. And so if we have the x2 and x1, and so if we assign to the 1 and 1, and so we can generate the output at the what? At the intersection point of this value. But the main problem is that how we can distribute this line in order to represent to the what? The probability. That's the main question or the main problem. And so the solution is simple. We should write the solution just like this one. Okay? And so the main problem is defined with the what? With this one. The problem is that the algebra and geometry produce exact solution. But in real life, we don't have this kind of property. The philosopher of the David Hume explained this. This is the expectation, not the solution or the exact point. In the deterministic way, in the what science, we can deduce or we can find the exact points, just like the equation solution. But David Hume created to the what? To the another philosophical thinking about the what? The solution or the outputs of the sum process. Okay? So, how we can model this notion in science or in artificial intelligence? We can draw to the what? To the axis, just like this one. And so, we can create the what? Solution to the 1. 1 maybe is a class. For example, to the what? The mass, or the human class, or the what? The Mehmet class. Okay? This is a decision in logic. But And so this should be, this is a line in this case, and so this should be interpreted as an area, just like this one. If we solve this problem, either we can deduce or decide it's Mehmet or not, or it's human or not, or it's computer or not. And so we can generate to the what? The probability region in here, okay? Just like this one. We can split, or we can remodel this line into the what? Into the area form of these terms, okay? Just remember the system dynamic, or the signal processing lesson, or the DSP, digital signal processing lesson. If we want to define or the model any signal, we apply to the what? To the convolution with a specific pattern, which we call it to the what? To the Dirac delta function, right? And so in the continuous domain, this probability rate is identical with the Dirac delta function, but in this case we split or interpret the one line which shows to the what? The decision of the Mehmet or not. In this case, for a classification problem, we interpret this line into the what? In terms of the area of these terms, okay? And so we can conclude that if this is the case, and so we can write this notion, we can interpret any data getting changed to what? Represent the outcome of the algorithm or decision of this logic, okay? But we have some conditions or the rules to define it into the what? If the logic is interpreted as an area or the probability rate of these terms, and so we should satisfy the two conditions, which is, first of all, if logic 1 is interpreted as area, then we must satisfy that the integral of the px dx must be equals to the 1, okay? This is the first rule, because we do not want to change our logic, just represent in terms of the area of the probability rate, which means that we should equalize to the total area, or the integral form of this probability must be equals to the what? Is equals to the what? Just like the Dirac delta function, guys, okay? So this must be satisfied. Second, if there is a chance to create this event, and so we need to say that the px must always be greater than equals to the 0 for all to the what? To the x, including to the what? Minus infinity to infinity values, or we can say it to the positive, okay? And so we can conclude that using these conditions, and we can transform logic state into the what? Into the probability one, okay? This is our case. So for that case, we need to build the model just like this one. For example, in normal case, but first of all we need to say that we need to build the model represent the probability of the data for a given distributions in here. But in normal case we can say that we have two parameters in here. Y is the output, X is the input, right? And so we can draw to the what the points just like this one. This is the data, and also we can assign to the what the hyperplane in here in the model of the what the h theta x is equals to what the theta 0 plus theta 1 x, right? And so this theta 0 and theta 1 is called to the what the system parameters or the model parameters in here, okay? But this defines to the what distributions or the data representation on this diagram based on what the hyperplane approximations. But the main question is that how can we find the model parameters of this distribution in probability theory? This is the main question. And so we need to define to the what to the new problems in here in order to understand that. The problem is that assume that we have this kind of data distribution y and x, and so we can draw at each point just like this one, okay? Each of them the data, and so this is to the what not only the x and also n is a sampling number. If we have the 100x, and so n is equals to the what 100, okay? So how can we model this diagram? First of all, the first solution is that we can use the multiple straight line. Can be used, right? For example, theta 0, theta 1, x, but we can add the theta 2 plus theta 3 x, blah blah blah. Or we can use the what? The MLP, multi-layer perceptron algorithm, in order to define these properties of these terms. Or we can assign to the what? The sinusoidal signal in here. This can be used, but how can be used? For example, the R model may be represented with the what? With this one. H theta x can be equals to the what? Sinus q p f x, and so this can be built with what? The theta 0 plus theta 1, and also we can assign the new parameters instead of f, and so theta 2, okay? And so if we solve this problem in the what? In the mean square error problem, and so we can define the gradient based on this model, and so this looks like to the what? The sinus signal, and so maybe we can find the theta 2, theta 0 and theta 1. But in this case we have only x data and n number samples, which means that this is the standard output form. But what about this? If we have been given is the n and x just like this one, if we have only input data in here, we need to derive from these parameters based on this one. This is only input, but in the previous case this is the output. But the user asks about to the what, how we can model the input based on this and sampling numbers. And so we can write that. Therefore, we need to derive most likely expected values and its deviation around this expected value. Okay, because we have only n and also have the x value, and so every data can have these properties in terms of the x and n, and so we need to find out what expected value. This is a probabilistic parameter and also the deviation, and so we can deduce to the what, to the deviation of these signals in terms of what these values. Okay, so how we can solve these problems? The solution is simple. As you know, assume that if we have only input data, just like this one, the n and x, and also these distributions in here. Okay, so what is the expected values of these terms? The expected values should be given just like this one. This is the expected value. But why this is expected value? This is the theta 0. With the previous example, this is the mu, and which is equals to what? Xi divided by n. This is called the mean or expected value in science literature. Okay, so this is the first solution. But what about this one? What is the around parameter in here? This around parameter is defined with what the variance values of this term, x minus mu squared divided by n, which means that this is the distribution rate of this signal, which we call it to the what, to the variance. Okay, and also a square root in here. This is the sigma value, and in science literature this is the standard deviation of this data set. Okay, so in final form we have, and also we need to drive this sigma and sigma value. We have mu variance, standard deviation px, with the condition of the what, the px greater than 0, and also the total integral form must be given y with the what, the summation form must be equals to the 1. Okay, and so the generalized solution can be written just like this one. The px for a given mu and standard deviation values must be equals to the what, 1 divided by square root of the 2 pi variance times exponential terms, which is equals to minus x minus mu square divided by 2 times square of the variance. This is called to the what? Probability density function. Okay, and so this is also called the normal distribution. Okay, in Turkish, in a short summary. Arkadaşlar bakın, biz bu zamana kadar hep böyle kesin modellerle uğraştık. Yani bize bir giriş verildi, çıkış verildi ve bunun arasında bir fonksiyon olduğu söylendi. Biz bunu varsaydık. Bunu lineer regresyonla, lojistik regresyonla ya da yapay zeka, yapay sinir ağlarıyla modellemeye çalıştık. Ama bunların bir tane sorunu var. Bir, bizim eğitim verisine ihtiyacımız var, modele ihtiyacımız var ve output'a ihtiyacımız var. Ve bunların hepsinin kesin olması lazım. Biz bunları istersek gözetimli, istersek gözetimsiz, supervised ya da unsupervised eğitebiliriz. Ama bunu yapmak istemiyorsak, yani kesin bir değer oluşturmak istemiyorsak, bir tane olasılık teorisini kullanarak aslında biz ne yapabiliyoruz? Kesin bir değer değil de kesin bir değere yakın değerler oluşturabiliyoruz. Ama bunu yapabilmek için neye ihtiyacımız var? Bizim bir tane lojik dediğim, yani aslında tek bir karar noktasının, bir sabit noktayı bizim bir alana yaymamız gerekiyor. Bu algebrada, yani aslında cebirde ve geometride aslında biz ne kullanıyorduk? Denklemleri çözebilmek için aslında çeşitli terimler kullanıyorduk. David Hume'e kadar aslında arkadaşlar bir tane olayı biz hep deterministik olarak gördük. Ama David Hume ne dedi biliyor musunuz? Bir tane olay gerçekleştiğinde diğer olayın gerçekleşmesini biz bekliyoruz dedi. Yani aslında sen bunu alana yayabilirsin dedi. Alana yaymak istediğimizde de bakın tek bir çizgiyi biz böyle bir alana yaydık. Ama bunun da bir koşulu var. Sen ne dedim ben? Hani bizim sistem dinamiği dersi ya da kontrol derslerinde biz ne yapıyorduk? Hep gidiyorduk bir tane sistemi eğer tanımlamak istiyorsak konvolüsyonunu alıyorduk. Ama ne ile? Dirac delta fonksiyonuyla. O Dirac delta fonksiyonu biz oraya koyduğumuzda biz oradan bir çıkış elde edebiliyoruz. Ya da sistemin kendisini anlatabiliyordu. O yüzden ben de diyorum ki burada bizim bir lojiğimiz varsa, bu lojikte birse ben bunu bütün alaya yayılabiliyorum. Ve bu alanın hepsi sıfırdan büyük olduğu sürece ben buradaki transformu gerçekleştirebilirim. O zaman normal durumda neydi? Bize verilen bir x vardı, bir de çıkış vardı. Bu x'e ben bir model atayabiliyordum. Ama ya bize sadece giriş datası verilseydi? Biz bunu nasıl modellerdik? Bunu modellemek için bakın arkadaşlar ya sinir ağlarını ya da şöyle birden fazla çizgiyi, hyperplane'i burada kullanmamız gerekirdi. Ya da buna benzer bir sinüzoidal bir sinyal oluşturup bunu parametrik hale getirebilirdik. Ama biz bunu modellemek istiyorsak, bakın burada ne yaptım ben? Benim böyle bir verim varsa, siz buradaki en olası değeri nasıl belirlersiniz? Gidersiniz bizim elimizde bir n tane veri var, x'lerimiz var. Bunların hepsini toplayıp neye böldüğünüzde biz ortalama değerini buluyoruz. Ama aslında bu ortalama değer ne demek biliyor musunuz? Bizim en olası beklediğimiz değerdir. Yani siz burada rastgele bir tane veri atsaydınız bu yine olası değerin etrafında bir değer çıkacaktı. O etrafındaki değeri biz neyle tanımlıyoruz? Varyans dediğimiz değerle tanımlıyoruz. Bu fonksiyon aslında arkadaşlar nereden çıkıyor biliyor musunuz? Bu fonksiyon bu verilerin üretilebilmesi için oluşturulan enerji fonksiyonunu minimize eden formülden çıkıyor. Yani biz buna ne diyoruz biliyor musunuz literatürde? Log likelihood, yani maksimum benzeşim optimizasyonuyla aslında biz ortalama değer ve standart deviation değerini bulmaya çalışıyoruz arkadaşlar. Türkçesi de buydu. Şimdi this px it looks like just this one, px. For example, this is the mu, okay? And so this is the mu minus delta, mu plus sigma, and mu plus q sigma, and also mu minus q sigma, okay? And so this is the deviation rate, but this probability is occurred with the maximum values of the mu, and also this going to the what, just like this one, but it's not true representation. Okay, this is maximum with the what, with this one, okay? So this is the probability of x for given mu and sigma square parameter. And so if we drive or generates the data around to what the mean values, this is the highest probability rate of this one, but the mu minus sigma is the what is less probability rate of these terms, okay? And so how can we show this diagram on the what, on the x graph, just like this one? And and x is given in here. Okay, and so what's the our parameters? Our data set are distributed just like this one. Okay, and so this is the what, this is the mu value in here, and also this is the range of the what, standard deviation. This is the standard deviation, and so this graph looks like this one, px, and also this is the what, this is the probability rate, so x values in here in terms of this one, and so we can draw this diagram just like this one. And also this is represented with the what, with this one. This is called the mu, and also this is the mu plus sigma, and this is the mu minus sigma. Okay, and so it's the highest probability rate of the what, of the x happening in that parameter or the values. Okay, so how we can create another terms in here? This is the one data in here, and so it looks like on the what, on the probability rate with the what, with these formations. But for example, suppose that we have x1 and x2 in here. Okay, and also we have a distribution of data just like this one. Okay, so this can be circularized just like this one, and also we can find to the what, to the mean values just like this one. This is the 4, and also we can assign to what, this is the 3. Okay, and in this case we can write that 2 data, 2 probability. So p1 x1 and so p2 x2. Okay, this is separate models, and also we can say that mu1 is equals to the what, is equals to 4, and mu2 is equals to what, is equals to 3. For example, sigma 1 maybe is given here 2, we don't know, but it's arbitrary number, and so sigma 2 is 3, 1. Okay, we can model this data distribution based on these values in here. Okay, and so we can model this function like its properties. If p1 x1 is greater than 0.7, and so it's around to the what, the mean values of the x1, and p2 x2 greater than 0.7, and so that's it. You can conclude that, for example, this is the Mehmet. Okay, or in scientific terms, if the p1 x1 is greater than p1 mu 1 plus minus sigma 1, and p2 x2 is greater than p2 mu 2 plus minus sigma 2, and then we can say that this is also Mehmet. But in this case we transform these values into the values, or we can identify the parametric definition based on these informations, and so we can classify the unknown data, or the x2 and x1, based on the what, based on the mu and standard deviation values of these terms. Okay, so any questions? Okay. And so, if there is no question, and so we can summarize the whole diagram just like this one. We write this in here. Okay. And so in Turkish. Arkadaşlar bakın, şimdi bizim böyle bir tane fonksiyonumuz varsa en beklediğimiz değer bizim mu değerimizde gelir. Ama mu'nun etrafındaki değerler, mu eksi sigma ya da mu artı sigma belli bir oranda aslında daha az olasılık gösterir. Mesela bizim burada mu'muz 4 değeri ise bu 4 değerini mesela biz daha çok görürüz bu sistemin içerisinde. Ama mesela 2 değeri sallıyorum şuradadır. 2'nin gelme olasılığı çok düşüktür. Ya da 1'in gelme olasılığı çok düşüktür. Bu olasılık diyagramı işte bize bir verinin ne kadar sıklıkla ve ne kadar oranla, olasılıkla gelebileceğini aslında anlatıyor. O yüzden de bakın ben aşağıya ne çizdim? Şöyle bir diyagramı aslında biz probabilistik olarak aslında şu şekilde gösterebiliyoruz. O yüzden bakın ben bunu iki boyut diye aldığımda dikkat ederseniz x1'in buradaki ortalama değeri 4, x2'nin 3. Demek ki ben bunu mu1 ve mu2 ile modelleyebilirim. Ve buna da bir tane varyans atayabilirim. Ve bu varyanslara dair eğer ki ben normal distribution yani aslında bu probability density function'ı kullanarak aslında eğer ki olasılık seviyesi 0.7'den büyükse ikisinde de ben ne yapabilirim arkadaşlar? Buraya diyorum ki yani bu klas eğer ki Mehmet klasıysa ben bunun Mehmet olduğunu söyleyebilirim. Ya da bunlardan düşükse Mehmet olmadığını da aslında ben burada ifade edebilirim. Bu tabi tek boyutlu varsayımlarda geçerli kurallar arkadaşlar. Şimdi bunun bir de çok boyutlu hali. Yani sınıflı hali var. Bizim burada sadece bir tane Mehmet klasımız var. Ama diyelim ki Ayşe olsaydı, Fatma olsaydı ya da işte atıyorum Osman olsaydı ya da atıyorum Onur olsaydı biz burada ne yapacaktık? Yani bir tane sınıf değil de birden fazla sınıf Mehmet, Ali, Ayşe ya da atıyorum renkler olsaydı biz bunlarla ne yapacaktık? Onun için de bizim özel bir modelimiz var arkadaşlar. O model ne? Hemen başlıyoruz. This is called Gaussian mixture model. This is the GMM. Okay? And so, this is the probabilistic model. Representing to the what? Mixture of Gaussian normal distribution. And so in this case we have more than one Gaussian probability P1, P2, P3, but these combinations creates the whole probability regions. In this case we have the probability or the collection of the summation of this probability must be equals to the what? Equals to the 2, because P1 the x plus P2 the x must be equals to 2. We have two probability, but if we combine this probability into the one model, and so we need to create the Gaussian mixture model based on this one. And so how we can model these terms? Assume that we have data like this one. For example, we have the x data with the n sampling rate, okay, x, and so we can build the what is x values, and also we have this sampling which is given in here, and then maybe this is the 3 and maybe this is the 7, okay. And so the model can be given by this one, but we can easily say that this must be class 1, this must be class 2, because the expected values are different to each other. We don't know the class 1 or class 2, but we should know that C1 and C2 are different. And so, in this dataset, we have k components, which we call it the components, which is equals to the 2, C1 and C2, having own mu k and variance sigma k square, and also the overall probability can be given by with this one. The px must be equals to the what if we have two classes k1 and k, and so pk times, and so normal distribution x for a given to the what mu k sigma k square. Okay, and so the k is the component number, and so pk is the weight of component, the importance of component, and so the nx mu k sigma k square is to what? The Gaussian distribution. Okay, so but can we select the four components in here? And so we can say that it's yes, we can create the four components based on these informations, but we don't need to do that, because in the Gaussian mixture model we can learn the data representations based on the X or the data set. But in this case we can see that we have two classes, and so the k components must be selected to two. But if I choose the 4, and so I can still model these properties, but this may be C3 and this may be C4. Okay, but the C1 and C3 are the same with the C1, with a slightly different or small different with each other. Okay, but the probability is to what is scaled between the 1 in this case. And so how we can write the equation of these terms? The conditions can be given by and so first of all we should write that the 0 pk 1, and also k must be equals to the 1 to the k pk is equals to the 1. Okay, and so the total, the weight factor must be equals to the what? To the 1. And also second, the n x for a given mu k and sigma k variance should be equals to what? 1 divided by 2 pi sigma k square times exponential is just like the normal distribution x mu k square 2 times sigma k square. Okay, these are the two conditions. But how we can learn this data distribution based on the Gaussian mixture model? And so the main problem is that how can we find the best pk mu k and sigma k square values? Okay, this is the main problem. And so the solution is simple. It's called the expectation maximization algorithm. Okay, and so what is the expectation maximization algorithm? This is an iterative algorithm to find out the pi k, mu k and sigma k. Okay, and so just look the name of these terms: expectation maximization algorithm. We want to maximize the expectation values of the Gaussian components based on the algorithms. Okay, and so in order to find out, the purpose is simple: find out the best pk mu k and sigma k square. Okay, and so in order to do that, the log likelihood function can be used for the GMM model. Okay, and so this is just kind of the energy function. The L is what I is equals to the 1, and so n and log k is equals to the 1 to the greater k pk times n xi mu k sigma k square. Okay, and so this is just kind of the energy function, but we utilize to the what the log operator, because the log operator can easily find out to the what to the exponential terms or the area forms on displays. For example, if we want to treat to the exponential function just like the Gaussian distribution, and so we can easily apply the log formulation, because in that case we do not want to multiply the terms, but instead of these things we can sum the exponential terms with the aid of the logarithmic operations in here. Okay. So but this is the iterative algorithm, and so the algorithm can be given by, firstly, initialize the what the parameters of GMM mu pi sigma, and also assign to the what initial values. I'm sorry. Initial values WK. This is called the responsibility. It is just kind of the gradient of the what the neural network. Okay, and after that, the each time the expectation step for responsibilities or the gradients of this probability rate can be calculated with that VIK, which is equals to the what PK times n xi for a given mu k sigma k square, right? And also the total summation of the probability, just like this one, pj times n xi for a given mu k sigma k square. Okay, this is the what the rates of probability or gradient. This is my term. Okay, it's not a scientific, but it's just like the gradient for a given exact parameter model. After that, we need to maximize in order to what? In order to model probabilities. Update the mu k sigma k square pk using w, right? These rates. And after that, compute L using updated parameters, and check convergence. Convergence is okay, and then we can say that we have reached the what the maximized point to be expected values for a given algorithms. Okay. So in Turkish, şimdi bakın arkadaşlar, bizim eğer ki birden fazla sınıfımız varsa ya da öyle bir sınıf görüyorsak, biz Gauss karışım modelini kullanabiliyoruz. Bunun anlamı ne? Biz birden fazla bu şekilde sınıf yaratmak yerine aslında P1, P2, P3 diye biz bunların hepsini bir yere toplayabiliyoruz. Bu Gauss karışım modeli de aslında bunları topluyor. Bakın bu örneğe 3'te bir tane veri toplanmış, 7'de veri toplanmış. Eğer ki ben burada 2 tane komponent seçersem C1 ve C2 diye, ben bunların ne olduğunu bilmesem de ben bunu modelleyebilirim. Çünkü ortalama değerini ve standart deviation'ını bulabilirim. Ama bunun hepsinin belli bir oranda toplanması lazım. Yani benim bir normal dağılım var. Ben bunu pk ile çarpıyorum. Çarptıktan sonra bunun hepsini topladığımda benim toplam olasılığım çıkıyor arkadaşlar. Yani her şeyi normalize etmiş oluyorum. Yanlış anlamayın. Burada 2 tane class seçmek zorunda değilim. 4 tane de seçebilirim. Ama ben bunu 4 seçtiğimde bu C2 ile C4, C1 ile C3 büyük ihtimalle aynı olacak. Ama sizin uygulamanızda bunlar farklı olabilir arkadaşlar. Peki biz bunları hangi koşullarda yapacağız? Bir kere pk değerinin kesinlikle 0 ile 1 arasında olması lazım ve toplamlarında 1 olması lazım. İkincisi, burada bakın biz normal aslında dağılımı kullanıyoruz. Ama biz bunları nasıl yapacağız? Buradaki pk'yi, μk'yi ve sigma k'yi nasıl bulacağız? Expectation Maximization algoritm aynı arkadaşlar gradient descent gibi bir öğrenme metodu. Ama olasılık üzerinden öğreniyor. Bunu yaparken de biz buraya bir tane enerji fonksiyonu yazıyoruz. Bu enerji fonksiyonu da log formunu alıyoruz. Neden? Eğer sizin eksponansiyelli bir teriminiz varsa, bakın burada toplama işlemlerinin hepsini biz neye alabiliyoruz biliyor musunuz? Çarpma formundaki her şeyi toplama işlemini alabiliyoruz. Çünkü eksponansiyel termle veriliyor. Yani eksponansiyel ifadelerde biz bunu kullanabiliyoruz. Algoritmayı nasıl kullanıyorum burada? Öncelikle parametreleri set ediyorum random olarak. Bu değerleri verdikten sonra responsibility dediğim şeylerim var benim burada. Bunlar aslında benim aynı katsayılarım gibi. Yani bir normal exact modelin ya da atıyorum hyperplane parametre modelindeki o linear regression'daki modellerdeki benim gradientlarım gibi bir şey arkadaşlar. Katsayı bunların hepsi. Bu katsayılarla ben aslında en uygun μk'ya, sigma k'ya ya da pi k'ya doğru aslında adım adım ilerliyorum. Hangi fonksiyonu minimize ederek? L fonksiyonunu minimize ederek arkadaşlar. Şimdi bakın, bu tabi bir konuydu. Bir de bunun çoğul hali var arkadaşlar. In English. What if we have 2D GMM model? This is utilized to handling the multivariate data as a mixture model, okay? For example, x1 and x2. This two data set, x1 and x2, and so in order to define to the Gaussian mixture model, we need to utilize the multivariate data, not only x. This is a 2D vector, and so it's defined with the what, with the px, which is equals to what, summation operator, k is equals to 1 to the k, and so pk times normal distribution x for a given mu k and sigma k in here. But in this case we should write to the what, the covariance matrix in here, because the x is the 2D data, k is again the component number, okay, and so but the sigma k is the covariance matrix instead of to the what, to the variance 1, okay, this 2D. And so the multivariate Gaussian distribution is given by with the what, with the normal distribution x mu k and sigma k value is equals to the what, 1 divided by square root of the what, 2 pi d times determinant of the covariance matrix times exponential term 1 minus divided by 2 times x minus mu k transform times inverse operator minus k x mu k, okay? But in this case we should utilize to the what matrix operations in here, just like this one. And also the same conditions are current for this diagram, which means that 0 pk 1 and also the k, bigger k, k is equals to what the pk must be equals to the 1. Okay, we can create the freely more components to represent the data which is given in here. Okay, and so the condition is the same for a maximum or expectation maximization algorithm, but before that we need to give a break, and after that I will show what the expectation maximization algorithm based on the what the 2D GMML, and then we will continue with what the Python PyTorch examples about it. Okay.